live.
Hello world, it's Siraj and welcome to this live stream. I'm so excited to be here with my new live stream setup. In this video, we're going to be predicting stock prices, so financial forecasting using Tensorflow.js. So what you're seeing right here is a graph of us predicting stock prices using what's called a recurrent neural network. But the actual aim of this video is to build a financial forecasting model using a convolutional network. So we're going to be looking at both. So I'm actually going to code out a convolutional network in the second half of the video. But in the first half, we're going to talk through some math. We're going to talk through the different models out there for financial forecasting. And I'm going to also answer some audience questions, because what is a live stream without some audience questions, right? So hello, everybody. Yes, good to see so many people here. I'm going to just sporadically be answering questions in 5-minute intervals, but really it's got to be related to the topic, right? Also in terms of a demo, I've got a great demo for us here. In terms of an actual visual demo, what this is a nice little web interface that I'm running off of localhost. And what this is doing is it's using a neural network to make predictions based on just simple binary data, right? So this is just an example of us being able to visualize what it looks like, right? So what we see here are the actual labels, right? The outputs 0, 1, 0, 1. And we have our predictions, which are right here inside of this tensor, and they look very similar, and they're going to get better and better over time, right? So that's the visual demo. But we're going to be predicting Apple stock. Okay, so that's the actual aim of this video. All right, so I want to start off by just answering 2 questions, and then we're going to go right into the code. All right, so question 1 is: should I do masters from the USA or wait to earn some money here and go for a PhD later? Okay, so I think, first of all, if you're going to do a master's or a PhD, it has to be at a really good school, right? It's got to be at a top 10 school. And if you're not going to go to a top 10 school, you might as well just do this yourself using the internet as your university. I mean, look at the most popular research institution in the world, right? DeepMind. If you look at their jobs page, they don't even have PhD listed as a requirement, right? What a PhD does is it doesn't just say, you are the greatest. What it really says is you have published actual research under the advisory of a professor or someone who is more knowledgeable. You can do all of that with the internet. You can find an advisor online. You can find educational resources online, right? So that's my thought on that. And one more question before we get into the code. Why not Python? Great question. So guys, JavaScript is really coming up in the machine learning space right now. Right now you can build a model in Python, import it to JavaScript, and vice versa. And so JavaScript is really becoming easier and easier to use for machine learning models. And you're gonna also start to see more developers build models in JavaScript. But most of the complex models are built in Python, right? So if I want to see someone build AlphaGo in JavaScript, and once that happens, and it will happen, then I think the playing field will be a lot more, level. Anyway, back to the demo, right? So time series data is starting to play a larger and larger role in our world, right? So examples include self-driving Teslas, right? So Teslas are constantly creating time series data, right? They're mapping out to where they are, and then these are 3D point clouds, and then over time, this comes out to be a time series, right? So by the way, a time series is a sequence of data points, right? Measuring the same thing over time. This could be 3D data points, 3D map points for Teslas. This could be stock prices. This could be smart homes measuring temperature changes over time. This could be open data publishing police departments of crimes happening at certain times. So time. Time is the key word here. As data changes over time, that measurement is a time series. So imagine sensors collecting data from 3 settings, right? You have a factory, you have a city, and you have a farm. And so it's measuring temperature, it's measuring the number of people in a room, it's measuring, the output of a factory. All of these are static data points that change over time, and because time is involved, it's a time series, exactly. Cool, right? So when it comes to financial forecasting, Arima is like the go-to model, right? So Arima is the go-to model, and it stands for autoregressive. It's an autoregressive integrated moving average. So the first question here is Arima a machine learning model? Arima, you can consider it a regression model. It is a regression model. Is it a machine learning model? I would say no, because it was handpicked for a specific use case, stock prediction, but you can't really use it for things outside of that, right? It was handpicked and hand created for a specific use case, whereas a model, a machine learning model, like say a support vector machine, is made for a more general use case. You can use support vector machines to classify cat faces. You can use support vector machines to classify stock prices, anything really. But Arima, I have a little algorithmic outline of what Arima looks like here. But what it comes down to is us approximating 3 different variables. The first variable is the number of autoregressive terms. The second variable is the non-seasonal differences needed for stationarity. And the third variable is the lagged forecast errors in prediction equations. So all 3 of these variables have their own associated equations. So we're calculating all 3. And so it turns out that this has been the most popular model for stock price forecasting. But I'm not going to go into that because with the advent of deep learning technology very recently, we can outperform models like that. And there is reason to believe we can, because there's a bunch of machine learning models out there, right? But neural networks, when given a lot of data and a lot of computing power, tend to outperform all of them most of the time. So why wouldn't they when it comes to financial forecasting? And you might be thinking, well, why don't I hear more about this? Because big banks and hedge funds, of course, they're not going to give away these models, right? This is not an open source industry, right? Finance is not an open source industry. We'll talk about Bitcoin and all of that later, but like in general, traditional finance. So these are very closed source models. Why am I making a video on this? Because I want you guys to win, and I don't care. It's not about that for me. It's about democratizing AI. So this is just, for me, this is like, I don't even care about this. I don't even care about like predicting stock prices myself, but I do care about you guys knowing about recurrent networks, about convolutional networks. And so this is a medium for me to explain that to you. Okay, so why deep learning, right? So like I said, when you look at the performance versus the amount of data, deep learning outperforms all of those other models when it comes to having a lot of data. So what is the obvious approach here? Now this is very exciting, right? So what is the obvious approach here? The obvious approach when it comes to time series prediction is to use a recurrent neural network. Okay, so I'm gonna explain how this works mathematically. So we have some input data, right? So first of all, we have a sequence, right? So we have a sequence of numbers. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we were going to use the first 9 numbers to predict what the next number is. It's going to be 10. And there is some function that describes this sequence. In our case, that function would be f of x equals x plus 1, right? Where x is the term that we are trying to predict the next term in, right? That's the function. And we can use a recurrent network to map out this function and learn what this function is. There's a function that represents everything in life. There's a function that represents how much attention you are paying to me. There's a function that represents how loud my voice is in relation to everything else. There's a function for beauty. There's a function for love. There's a function for everything, and we can learn these functions using machine learning technology, right? So when it comes to recurrent networks, normally with feed-forward networks, we are feeding in every new data point, right? So we have term 1, term 2, term 3, term 4, and that's it. But recurrent networks, they're fed in not just the new data point, they're fed in the hidden state, the learned weight value, that matrix that's initialized as just 0, 0, 0, 0, 0, 0, right? Just all zeros, that's getting optimized over time. It's fed that in as well. So it's the input and the old weight matrix from the last time step that are both concatenated together, combined together, and then fed to the model, and that just keeps repeating. And because the model is fed in the previously learned matrix values from the weight, from the last time step, it's considered a recurrent network. So mathematically speaking, we have our input x of t, okay? So where t is the time variable, where we have x of t equals w of t, which is the input data, plus s of t minus 1, where that is the hidden state from the last time step. So it's fed both together. That's the input. And so when it comes to the hidden layers, for as many as we have, and that's what this sigma value means, right? This big E, it's sigma notation. It means take this operation or these sets of variables here and whatever operations there are and add them up for as many as you have. So in our case, that would be the number of data points. So we're going to take that input value, x of t, like we just talked about here, and we're going to multiply it by the weight value, right, at that time step. And that's going to give it, and the function of that operation is our hidden layer, okay? And that's why it's called s of t. And that's why up here we say s of t minus 1, because this is our new hidden layer, our new hidden state, and this is our old hidden state from the last time step. And so now we have this hidden state, we can use it to compute an output. So we take that state, s of t, we multiply it by the last weight value, v of k, and we do that for as many inputs as we have. That's why the sigma notation is there. That's our g of x, x is this function, and the result is our output. And the output is a label, or it could be the next term in the sequence, and that's y of t. Okay, so that is a recurrent neural network. It's a universal function approximator that is learning a function by being fed in new data points as well as what it has learned in the previous time step. And this is the go-to strategy for regression models, right? Predicting the next data point in a sequence. But there is a problem. And before I talk about that problem, I'm going to answer two questions again from the live stream. Okay, so the first question is, how old are you? That's not related, but I'm going to answer it. I am 27 years old. Can you believe that? I'm 27 years old. What that means is if you are 27, younger, older, age doesn't matter, right? Nothing. We live in an absurd reality, right? Where credentials, age, where you're from, all of that doesn't matter anymore. All that matters is how motivated you are because you've got the internet. You can literally do anything you want now. You have the internet, you can become a world expert in AI as a college dropout. You can do anything, right? So that's the reality we're living in. I'm 27. And one more question about AI specifically. Can we use reinforcement learning for time series data? You guys are speaking my language. Oh, did someone just donate some money? 100 pounds or euros? So I got to answer this question. I didn't even know I enabled this, but what was the first question? Time series? Yes, you can. You can. And I have a video coming out on that tomorrow. Rupees, okay. Is learning, so Debanik asks, is learning TensorFlow required or being able to use Keras is fine? Look, the more you learn, the better you're gonna be, okay? But I would say, yes, learn TensorFlow. Don't just learn Keras. Start off with Keras because it's easy, then learn TensorFlow, then learn, just progressively get harder and harder over time. Don't just start with like buying a giant linear algebra textbook and saying, I'm gonna start learning machine learning today. And then you're like learning about things that you don't necessarily need for machine learning, right? Just give yourself these small incremental rewards to keep you going on the learning path. This is what I do, okay? And as you get those rewards, you're going to become more and more confident in this space because in the end, a degree, a credential, a PhD, all that is you being able to tell yourself that you have learned something, right? So as long as you can tell yourself that you've learned something, you will be more confident to learn the next subject in the future. Right, okay, anyway guys, so back to this. There's a problem with recurrent networks. The gradient that's computed to optimize the network over time, it diminishes, it vanishes slowly, right? Because forward, so there are two processes in a neural network, okay? I'm about to go into the math right now, so you better hold on to your butts. Okay, this is some good stuff. When we are forward propagating the gradients, right? We're doing input times weight, add a bias, activate, right? Input times weight, add a bias, activate, and we just repeat that over and over, and that's the feed forward process until we get that output value. We have that output value, we compare it with our actual label, we compute an error. We use the error to compute the partial derivative with respect to our weight values, weight 1, weight 2, weight 3, in the reverse order. So we go backwards. We use that partial derivative to construct a gradient, and a gradient is a list of partial derivatives that we can use recursively to update those weight values using that gradient. But the problem is over time that gradient gets smaller and smaller and smaller and smaller and smaller until it's not, so the layers at the beginning of the network aren't updated as much as the layers at the end of the network. And this is a problem because we want that gradient to not diminish over time because we want our network to learn sequences. So someone came up with a solution called an LSTM network. What this is turning one equation into three equations. That's what it is. And we can talk about, you know, gates and all of that, but what it really comes down to is this set of four equations here. The three equations really just make this one equation. So I'll talk about this in a second. What we are really doing in an LSTM network versus a normal recurrent network is we are replacing one weight with three weights. Right, we have that input times weight. There's a weight that's a matrix at every layer, a group of numbers that are learning over time. What an LSTM is three weights. We have an input gate, a forget gate, and an update gate. And all of these gates are mini perceptrons. They're mini neural networks, and they all have their own weights. And they're represented by these equations. So what we do is when we have an input and it goes into the first layer, which is an LSTM cell, this is a cell, all of this, four equations, we multiply the first weight by the hidden state times the input. We apply a sigmoid activation function to it, and that gives us a value z of t. Now we take that value, we do the same for that. So that's we have an input gate, we have a forget gate, we have an update gate. So we do that for the input gate, and we have a forget gate. We multiply that weight by the hidden state times x, and that gives us our sigmoid. We have the third weight value, our third gate, weight value times hidden state times the previously computed value here, times the input, and we apply the tan h activation function to it, not the sigmoid. And this gives us h of t with the squiggly over it. And we use all three of those values here to compute the final hidden state. So what are we doing? First of all, if this is confusing, that's okay. I'm going at it right now. What are we really doing in every layer of a neural network? We're computing a hidden state. So that's what this is, this hidden state. It's the same result. We're computing a hidden state, but we're using three weight values instead of one weight value to compute that hidden state. And that's what that is. And we repeat that over and over again. And what this does is inside of those three weights, the gradient is being captured, right? It's learning what to forget, what to remember, what's relevant in the sequence. And that's the whole idea behind LSTM networks. So the gradient doesn't diminish, it doesn't vanish, it stays static over time, which is what we need. We need full upgrades for all of the weights in our network. So when it comes to predicting a sequence, and the sequence is Apple stock, we can have a sliding window, right? So we have W, which is some interval of prices over time, and we say WT plus 1, and that's going to give us the next one. So given these prices, what are the next prices? So we can think of it as sliding a window across a time series. That is what it is. So when we look at feed-forward network data, we have the number of examples, right? How many data points times the number of inputs by the number of inputs. But when it comes to recurrent network data, we don't just we have a third dimension, time, right? Time matters. And we have the number of time series examples, the values at every time step, and the number of time steps. So it's a three-dimensional input for this recurrent network data. It can be more actually, but it comes down to having time as that third dimension, and we can squash the dimensionality using a dimensionality reduction technique to do that. Okay, so we have some smart people in this chat room, by the way, guys. I'm so proud of just the level of interest in AI and just just you guys are really impressive people, wizards. Okay, so right, so we can think about W. So W is that window. We can think about it as the sum of all of those values before it. So W of 1 is the sum of all the values before it. W2 is sum of all values before it, right? And so inside of our LSTM, we're taking that input, we're giving it to the LSTM, and it's going to output the next value in that window, WT plus 1. Wait, W subscript T plus 1, so the next time step. And so that's called backpropagation through time. When we're applying backpropagation to recurrent networks, it's called backpropagation through time. So I'm going to build a model at the end of this, but I first want to just show you really quickly a simple LSTM model in Python. We're going to get to the JavaScript. I'm literally going to build that. But I want to show you a simple Python model first. What we do is we create this data set right here using this data preprocessing technique. We have our input data, we have our output data. Data X is our input, data Y are our labels. We fix a random seed because these values are generated randomly inside of this test example, but we want it to be reproducible. That means we want the same random values to be generated every time we run this for testing purposes and debugging purposes. We'll load up our data set. We'll use pandas to process it. By the way, pandas, great Python library for data preprocessing. We'll normalize it so it's all on the same scale. We always should have all of our data on the same scale between 0 and 1 or whatever, so that it's easier for our network to find the relationships between all of these data points. We don't want one feature to be between 0 and 1,000 and another feature to be between 0 and 1, right? That's way too big, right? We don't want one feature to be a list of strings and another feature to be images, right? That's completely different. We want that data to be similar. We want it, so that's where normalization comes in, so that our network can see, hey, this is all just data. This is all just numbers that's on the same scale. I can easily see the the line of best fit, whatever it is, between all of these features. We split that data up, we reshape it, we feed it, and here it is. Here is that complex LSTM network that I just talked about. We can do this in 5 lines of Keras. That's where we are today. Obviously, if you want more detail, then you can add in TensorFlow or NumPy if you're going to be a baller. You're just going to build this straight out of NumPy. And then we make a prediction, right? So model.predict, train data, model.predict, testing data. And then we can graph it out. And this is what it looks like, just like this. It seems, the red is our prediction, blue is the actual, the real data, the time series. Works well enough. Now, to the good stuff, what we've been waiting for. So I'm actually not going to use a recurrent network. I'm going to use a convolutional network. You might be thinking, what? Siraj, convolutional networks, they're used for images. Why would you use them for sequence classification? That's crazy talk. And before I answer that question, 2 questions from the comments. Here we go. All right, 2 questions is asynchronous actor-critic reinforcement learning practical for trading? Thank you for your live performance. It's quite some effort to improvise. Thank you. Yes. Okay, so short answer is yes. Reinforcement learning in general is a very underutilized technique for financial forecasting, and it's a very interesting research problem in general. You have multi-agent networks. You can think about other traders as agents. You can think about, there's a lot of different ways to frame this in a reinforcement learning context that hasn't been before, where your environment is the prices, and the algorithms and the traders, the humans, are all considered bots. And you're interacting with this environment inside of this, what is considered a Markov decision process that's partially observable, because you don't know the values of their account balances or things about them in general. So that's why it's partially observable, and that makes it a very interesting research problem. So yes. 2, how will you save your trained model? We're going to save it as a PB file, protobuffer, right? This is the standard for TensorFlow, it's the standard for Keras, and it makes it easier to export models between different frameworks and languages even. You can train a model in TensorFlow with Python and then use it in Tensorflow.js with 1 line of code, and vice versa as well. Very great for portability. Back to convolutional networks, right? So convolutional networks are generally used for image classification, right? And they're used for image classification because they outperform most other models when it comes to image classification. And what it comes down to is, again, it's a series of matrix operations. That's it. That's what all neural networks are. They're a series of matrix operations: add, subtract, multiply, divide. Simple operations between groups of numbers that are called matrices. Input times weight, add a bias, activate, right? So here's how a convolutional network works. So we can think of an image as a matrix, right, with RGB values, right, between 0 and 255. An image is really just a matrix of numbers that specify how red, how green, how blue every pixel should be. Now, in the context of a convolutional network, when we feed in these images into the model, we don't consider it a 2-dimensional matrix. We consider it a 3-dimensional matrix. Why? Because the 3rd dimension is RGB. Right? So RGB is 1 dimension, and then the other dimension is the width, and the 3rd dimension is the height. So width, height, RGB. There are 3 dimensions. And so that is what a convolutional network is used to, a 3-dimensional tensor, right? Because a tensor, so little linear algebra terminology here. A scalar is 1 number. A vector is 2 or more numbers. A matrix, okay, so let me start over. A scalar is 1 single number. A matrix is a row and a column of numbers. A tensor is a generalizable form of all of them, right? So a tensor can be a scalar, a tensor can be a matrix, it can be a vector of size n to the 100-dimensional. It could be 100 dimensions. So a tensor is just the most generalized form of saying all of this. That's why TensorFlow, that's why it's called TensorFlow, because tensors inputs are flowing through different operations in a computation graph, and that's a neural network. So we have our input, and so here's how it works. The convolutional networks have it's 3 operations that are repeated over and over again. Convolution, ReLU, pool. Repeat that. Convolution, ReLU, pool. What the convolutional layer is it's a flashlight that slides over that input image and it computes a filter. Here's what I mean. So we have our receptive field. Okay, so what that is it's a matrix, and we are continuously performing the dot product on that input by that filter, and we're sliding over the image. So that value plus 1, that value plus 1, that value plus 1, go down again, that value plus 1, that value plus 1, that value plus 1. What's up? Yeah, that value plus 1, that value plus 1, that value plus 1, right? And it could be plus 2, that's the stride. So the stride is the value that says how big are the intervals that I'm sliding this. It could be 4, it could be 8, right? But we're computing the dot product between this randomly initialized filter and that input value, and that input matrix tensor. And it's computing this output, right? That's our output filter. And we repeat that, so that's the convolutional layer, right? So once we have computed that filter, we apply an activation function to it called ReLU, which stands for rectified linear unit, which is, and the equation for that is y equals max 0x. Y equals max, parentheses, 0, comma, x. What that means is it's negating all of those negative values and that could be computed. So everything's got to be positive. And what this does is 2 things. 1, it makes sure that the network can learn both linear and nonlinear functions. So it's a universal function approximator. And it makes sure that the gradient doesn't vanish. So ReLU was also invented as a way to prevent the vanishing gradient problem that we talked about in recurrent networks. And so once we have that ReLU, then we can do pooling. And so what pooling is us saying, this is the convolving part, right? This is the flashlight part. It's multiplying by the dot product, by that filter, by that input over and over and over and over again. And then we have the output filter. And then, so what pooling is us saying, what is the best, I'll talk about best. What is the best values from every region of this filter that we've computed? And that's going to be our output. And what this does is it reduces computational complexity, which makes the model faster. And so we see here is like, let's say this is our filter here with single depth slice. If we perform max pooling, so that's one form of pooling, we take the maximum value from each region. In this region, it would be 6. In this region, it would be 8, 3, 4, right? You see what I'm saying? And so what's happening is, as we move through this convolutional network, there are more and more filters that are being computed. It could be like 4, 16, 32. But each of these filters are smaller and denser, and they're more specific to certain features, right? So it's this level of abstraction where the biggest filters are like head, and then it goes to like, eyes, shapes, curvature, like very little details. And the output then is going to be one of several classes, right? So class values. Is this a car? Is this a truck? Is this a plane? So that's a convolutional network. Why apply them to time series data? Okay, so 2 reasons. One is, so a recurrent network was invented to make sure that we take the context of the previous sequence into account, right? So if we're going to predict the next word in, say, a sentence, I'm going to the bank to deposit some. So you know what I'm going to say, money. But a machine doesn't necessarily know that. We have to take the context of bank, today, me, what I've done in the past, into context. So the recurrent networks are really great at remembering the past. They're not great at but taking the future into context as well. So if we have some testing data, we know what the 10 next points should be. That doesn't matter in a recurrent network, only the past matters. So convolutional networks are good at seeing both sides, are better than recurrent nets at taking into account both sides of the timeline. Second of all, convolutional networks are faster. They're less computationally expensive. So you can run them on big data sets in a much faster timescale. Third, convolutional networks take into account locality, right? So the locality of features, because this is a good thing when it comes to images. The same feature that matters locally, like say, the blackness of my eye, also matters here, right? So if it sees like white in this shape, it'll know, like locally speaking, well, there's probably black, and it sees here, oh, white, there's probably black. Whereas, recurrent networks are more generalized into taking the entire data set into account. Whereas convolutional networks focus on the locality of features. So when it comes to prices, for example, what Bitcoin's price was 5 years ago is irrelevant to what its price is going to be now, if you think about it, right? Now, everything is different, right? So that can apply to stocks as well, right? So high frequency trading, for example, right? Making trades at nanosecond timescales. That is all about locality of where we are right exactly now and what's happening. And so that's why convolutional networks are better at. They have fewer sequential calculations, they tend to be more computationally efficient, and they focus on not looking at the data holistically as a whole, but more capturing those, and to be specific, temporal relations from the beginning of the time to the end of the time, all right? So, and here's the little complexity chart. Okay, so 2 more questions and then I'm gonna code. Code time is coming, okay? So what are the questions here? Can you share that notebook? Yes, it's actually in the video description. And the second question is, why should we not add even more weights than the 3 in LSTM? Because, as Andrei Karpathy says, there is a diminishing return to adding more layers, right? So up to a certain point, generally like 3 to 4, 5, 6 layers, you have marginal returns, but then after that, it's a diminishing return, and you're adding computational complexity because it's all about trade-offs. Okay, so now let's build our recurrent network. Okay, so we're going to build this using Tensorflow.js. Now, I want to say that we have built out this front end. So the front end I talked about is here. What I want to do now is actually build the network itself and focus on that because that's the most important part. With Tensorflow.js, you just import Tensorflow.js in your HTML and that's it, right? So you don't even need to install it really. It's just learning it. As long as you have an internet connection, it's there. So we have that. So let's build our convolutional network. That's step 1. We're going to build our CNN. We'll call it this constant build CNN that we're going to use later. So this is going to be a function of the data that we feed the model, okay? And so that's what that is. So what are we going to do inside of this function? Well, what we're going to do is we're going to return a promise. And you might be saying, well, what's a promise? A promise is it represents the eventual result that we're going to have of any asynchronous operation, which is in our case is going to be the data that our convolutional network that we compute. So it's a placeholder, okay? So it's a placeholder, and then we're going to compute a result later on. And so that promise's value is going to be a function, our neural network, and function, great, new promise, function, resolve, reject, cool. Now let's start building this thing. So the first thing we're going to do is we're going to say we have our model using Tensorflow.sequential because this is a linear stack of layers, layer 1, layer 2, layer 3. For more complex models, we would want a nonlinear stack of layers so it can branch in 2 different directions. A lot of models that incorporate attention mechanisms can do this, but we're going to start off very simple with a simple sequential linear stack of layers. So now we can start adding these layers using the tf.layers function, right? So each layer, the layers is a high-level API. It's like Keras, but for JavaScript, okay? So we're going to say, well, our first layer is going to be our convolutional layer, right? Because our convolutional networks have these layers. And so the first layer, we're gonna have to specify some of these values, and I'll talk about them in a second. We have our filters, we have our strides. What else do we have to specify for a layer? We have our activation function, we have our kernel initializer. And right, if you look at the TensorFlow documentation, all of that is there. And so I'm just kind of like, based on what I've seen, doing that, right? So for our input shape, what is our data going to look like, by the way? So our data is going to look like by the way, I can't believe I didn't even show that. This is what our data looks like. We have the dates and we have the closing price, right? So that's what that is. So we have one price for the input data. So this is our input, the date, and the price is the output. That's what we're predicting. And so because convolutional networks prefer a 3D tensor as input because they're used to images, what we're going to do is we're going to turn this date into a three-dimensional tensor, whereas one dimension is the year, one dimension is the month, and one dimension is the day. And so it's a 3D tensor as input. The label is this price. Okay? So when it comes to our input shape, we're going to say, assuming that we have that the dates, because we have the data that's being fed into this CNN, which are the the input data. We're going to say it's going to be the length of the dates, by 1. Now, when it comes to our kernel size, let's say we want 100 of those data points to start off with. Filters, generally there are multiples of 8, 16, 32, but let's start off with the small one, 8. Strides as well, those generally increase or decrease in size as we go further along. So you want to start off with a bigger number and then decrease it over time. So I'll start off with 2. Activation, of course, like I said, ReLU. And kernel initializer is called variance scaling. What do I mean by variance scaling? This basically is a weight initialization technique. It's also called Xavier in some contexts, and it tries to make the variance of the output of a layer be equal to the variance of the inputs. And this reduces overfitting, so it's called variance scaling. I can make an entire video on Xavier initialization, by the way, but we're going to call it that. That's our first layer. Now for our pooling layer, like we did our convolution, we did our ReLU, and now we can do our pooling. We'll do tf.layers.max pooling. That's our 1D. And now we can say, well, what's our pooling size going to be? We'll start off with a big pooling number, and then for the next pooling, remember, we start off big and we get smaller. And generally, pooling is like, they're in intervals of 100. So I'll do 500. I'll also answer some questions in a second. The striding, like I said, is going to be, well, let's just say 2 again, because it's like a part of the same block, in convolution, ReLU, pooling, and then it's going to change over time. So let's say strides are 2. And now we'll just repeat this process again. So we'll say model.add for the next layer. The kernel size is going to be much, much smaller. So let's pick something much smaller, 5. What did I say about those filters? The filters increase, right? Because there are more filters, but they're smaller as we progress through the network. Filters are going to be 16, strides are going to be 1 because it's smaller, ReLU, and variance scaling again. We'll repeat that again with one more pooling layer. And it's going to be, like I said, the pooling is going to be smaller. Let's pick 100. Strides are going to be 2. And lastly, we want to add R. And I'm going to answer questions right after this. Lastly, we're going to add R. What are we going to add? We're going to add our model tf.layers.dense, our fully connected layer. That's what I'm trying to say, our fully connected layer, because we're going to now take all that data and make a single class prediction, and that's what our softmax layer is going to do. It's going to output class predictions, which is going to be, in our case, the next price. So dense, and that's going to be units 10. That's the thing about it's fun because you get to see what's going to work and what doesn't work. Activation is, of course, a softmax function. And Now we can return all of that as a resolve, thanks to the promise that we've made at the beginning. We're going to return the model, we're going to return the data. Return the model, return the data, and that's it. That's for our build CNN function. We take 2 questions. Missed comma on line 12, thank you very much. Data.dates.length, thank you. Boom. Now where were we? Why don't you use the adaptive theme on Sublime Text? Because I don't have time. And can I run these on CPU? Yes, you can. That's the great thing about JS. You can run these on the CPU. All right, so. Yeah, lots of questions. Okay, so now, where were we? Now we're going to train this thing. Right. So step 2 is to train our model. We built our CNN, now we're going to train it. So we're going to say CNN equals function model, given our data and given the number of cycles or training loops. We're going to say, let's split out that data. So we have that input data into its own tensor, each of them. So we have our dates. We have our testing data. Testing data is going to be tf.tensor1d again. We have our data.test times, and we have our out equals model.get layer. And we want to get that last dense layer so we can make the actual prediction, right? We want to make that prediction in a second.
Colons on 12, 15, 16.
Thank you, thank you, thank you. Colons on 12, 15, 16. 15, also 14. See guys, when I'm teaching and I'm coding, I'm gonna get better at this. It's been a while, it's been a year since I've done a live coding stream, but thank you very much. Yeah, cool. Colon, 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 colon. Or period, period, or comma, comma, comma. Good. Yep. Yep. Great. All right, where were we? Right, so model helper is going to be our helper function for our model. And now we can train this model, and this is going to be inside of a promise again. You know, if it doesn't work, we have some. It's kind of like a try-catch loop in a way. Okay, so we're going to try this out. Speaking of try-catch loops, we're going to say compile the model, and now we've built the model. We want to run this thing using the optimizer, a stochastic gradient descent, which is the go-to optimizer for neural networks. Our loss function is going to be probably the most popular one, binary cross entropy, which is going to compute our error value. And our learning rate is going to be a very standard 0.1%. Most often learning rates are at 0.1%. The thing about deep learning, by the way, guys, is we are basically just jumbling up some of these parameter values, and we are learning over time. So that's the art of deep learning, is saying, I think these are good strides, I think these are good filters, I think this will work, compile, run the model, see the results, and then change those values as you see as necessary. And sometimes you'll change those values and you'll break the internet because you just beat everything else. And that's the really exciting part about deep learning. And so once we've compiled that model, we're ready to train it with the fit function. Okay, so we're going to say, let's make sure to reshape that input data so that it's in 3 dimensions. And do that one more time. Dot reshape 1960. And I will wrap at the end of this, so stick around, by the way. 1 batch size, and then the number of epochs. How many cycles do we want to run this for? And now we can tell. I know I gotta fix this up in a second. Just hold on. I'm gonna fix all these little parentheses and brackets, et cetera, et cetera. We can tell our model it's running, it's running, whatever we want to say, and then print out that prediction. and then so we have a catch loop as well. We have our catch loop is going to be resolve, print, whatever the exception is. That's for our exception. And now we can execute this. So we can say prep data for the function and take the result. We're going to build our CNN using the result. And then, once we've built our CNN, built function, then we can say, no, and I'll answer questions in a second. CNN built.model built.data 100, then function e print done. So it's like that. Now I will purchase the license at some point. Okay, so I've probably got some serious errors here. Let's see. Say Python. Hold on, where were we? CD scripts. Where were we? CD public. CD scripts. Python 2b. CNN.js. Invalid syntax on line 1. Oh, you know what? Sometimes with hold on a second. GitHub time, guys, because we are running out of time in this live stream, and battery, and everything. But yeah, anyway, here's the GitHub link for you guys, by the way, which I already have here, which you guys should have been following along with anyway. Anyway, public scripts, boom, here we go. And it's very well commented for you guys as well. So definitely check this out. When it comes down to it, given either the logical data or the Apple data, it's going to be predicting the next data in the time series. And we can wait, and there we go. And so that's for test data. We're pulling from the Apple API, and then we made this JSON file right here, and then we trained it on that. But yeah, convolutional networks, super useful for time series forecasting. Also, I want you guys to say a subject. I'm going to rap about it. All right, so just say some subject. In the meantime, I'm going to answer 2 questions. Siraj, you need a crowdfunding campaign for a Sublime license? Yes. No. Don't worry about it. It's kind of like a meme now. Like I just never get Sublime. And then lastly, what are the questions? Anyone here from Amsterdam? I used to live there. Hoe gaat het? And should I know tf.js before seeing this video? No. I think this was simple enough. As long as you've recognized, Keras or TensorFlow, and you've seen linear models, then you can get this. Right. So thoughts on reinforcement learning for time series? Of course, I like it. Medical image analysis. I have a great video on that. Search medical image analysis. And stationarity, how important is it for LSTM? It's not as important for LSTMs as it is for Arima. So Arima focuses on that, whereas LSTMs more focus on features across the entire, so it's a holistic overview of all of that sequential data. Rap about egalitarian technocracy. Why did I pick the hardest one to mention, seriously? Egalitarian technocracy. All right, here we go. It's freestyle. Turn up the sound. Oh shit, I don't have sound. Could you play a beat from there? Anything, just pick an instrumental. We're about to do this on YouTube. Just search rap instrumental. Okay, here we go with the wrap. It's coming in 5, 4, 3, 2, 1. All right. There we go. Oh, I got it. Sick trap beat. You say I need a technocracy. I'ma give you a democracy. I'ma show you how to break out of monotony and show you the life that you can't see. I'm trying to go and fly so free outside and see all my enemies telling me that you can't do it. Hold up. I'ma break it down, show you that governments don't mean anything. It's the internet. We got a new techno utopia. It's like, man, I'm in it. I'm in it. I'm out of it. I'm back in it. You don't even see because I'm beyond it. That's it for this wrap. I just wanted to do a little 5-second demo to keep it interesting, guys. So that's my wrap for today's video. I hope you like this video. Share. The best thing you could do for me is to hit the subscribe button and tell your friends to subscribe. That is a single metric I care about. Subscribe. I'm trying. This audience is growing, but it's not growing nearly fast enough. We're trying to get to the top. You know what I'm saying? 1 million subscribers by the end of the year. That is the goal, okay? It's a very unrealistic goal, but I'm an unrealistic person. Okay, so thank you guys for watching. I love you guys. You're the reason I do this. And for now, I've got to go take a plane to Houston to visit my parents. So thanks for watching.